The world is complex and messy because multiple factors constantly affect each other. That's why univariable models fail to describe complex relationships. In this video, we'll explore multivariable models which provide a more accurate representation of reality. Expect to learn how to effectively visualize model results, how to extract the most knowledge out of your multivariable models, how to interpret them correctly, and much more. The wage dataset in the yuzaR package can help us determine which factors influence our salary. We'll clean the dataset a bit and select 100 random people from each educational group for our multivariable linear model. To build the model, we'll use the intuitive LM function. Within LM, we only need two arguments, the formula and the data. The formula has two sides, left and right. On the left side of the formula, we'll place our outcome variable, which has several names. On the right side of the formula, we'll place our predictors. Unfortunately, predictors also have many names. We'll take only two numeric and two categorical predictors to learn how to correctly interpret complex models. But we can't just jump into interpretation without making sure the assumptions are satisfied. Otherwise, we'll risk making misleading conclusions. The check model function from the performance package is so intuitive and so powerful that once you realize what it does, you'll never use anything else ever again. Because check model functions checks all assumptions visually at the same time. Looking at the assumptions, we could immediately conclude that the model predicted lines fit the observed data pretty well. The linearity assumption likely holds because the reference line is flat and horizontal. The variance seems somewhat uneven, suggesting heteroscedasticity might not be entirely absent, but there is nothing dramatic like a cone to see. There are no influential observations or outliers since the points stay inside the contour lines, probably because we cleaned the data beforehand. All four predictors are not multicollinear, and while the year's coefficient seems a bit more uncertain, the variation inflation factor itself is still low, thus I'll accept that. Finally, the residuals appear normally distributed, as they stay inside the confidence intervals of the regression line, indicating that our data is generally normally distributed, so that we don't need to check the distribution of numeric variables separately. Oh, and by the way, if you have a lot of data, and by a lot I mean even as few as 50 observations, it's essential to check assumptions visually, like we just did, rather than relying solely on statistical tests. Why, you ask? Well, statistical tests can sometimes yield significant results, suggesting that assumptions are not met, even if they actually are. Let me illustrate this with two examples. First, the Shapiro-Wilk normality test mysteriously detects not normally distributed residuals, even when they are perfectly fine. And secondly, the Breuer-Spagan heteroscedasticity test detects non-constant error variance, while it is acceptable in this case. Now, since the assumptions of our model are satisfied, we can visualize model results. And by results, I mean visualize model predictions. We'll first use the ggEffect function from ggEffects package to look at the predicted averages. This will give us an intuition about our data. For the numeric variables, ggEffect nicely provides a few values for us to see the trend and examples, instead of giving only the average. It's also important to notice that those averages are averaged over the categories of other predictors.
Now listen to me very carefully.
Averaging over the categories is very important, because most of other functions use average for numeric, but the first reference levels for categorical predictors. Let's take the ggPredict function as an example. It adjusts the age for the average year, but only for the first education and the first job class levels. This results in an estimated earnings of 96K at the age of 60, which is absolutely correct for individuals working in a factory without any education, However, it's completely wrong for our dataset, which includes 5 different education levels and 2 different professions. If we average over all these categories, we'll find that the expected earnings are 118Ks, significantly higher than 96. So please be aware of what you're asking the model for, otherwise you might make inaccurate conclusions. By adding the plot command to the ggEffect function, we can plot estimated averages of all predictors separately. Additionally, when we use the plot grid function from the sjplot package on top of both ggEffect and plot, we can combine them into a multiplot. This allows us to create a fancy plot in the format, quality and size of our choice that tells us a compelling story about our dataset. Specifically, the plot reveals that salary increases with age. As individuals get older, their earnings tend to rise. The salaries also increase over time, from 2003 to 2009. Job transitions seem to matter because shifting from an industry job to an IT role leads to salary growth. And finally, education level matters a lot, since each step up in education corresponds to an increase in earnings. Cool, right? However, these plots don't directly show whether these salary increases are statistically significant. To address this, we need a fancy table with p-values alongside our fancy plot. To create such a fancy table, we'll use the table regression function from GTSummary package, where we only need 2 arguments: the model name and the add pairwise contrasts equals true argument. The rest of the options are optional and there are settings for everything you might need. If you are interested, I've already covered this in a separate video dedicated solely to the GTSummary package. For now, I would only point out 2 advantages of table regression that greatly improve the quality of our results. The first advantage of the table regression function is that it displays all pairwise comparisons for categorical predictors, instead of only comparing everything to the reference category, which is what the summary function does. For example, in the case of education predictor, we would get 10 post hoc tests via the table regression function instead of only 4 with summary, resulting in 2.5 times more inference. Another advantage is that we can easily save our fancy table in a publication-ready Microsoft Word or PNG format. This will save you a lot of time and effort while writing a paper, and will allow you to easily edit your table without the need to change anything in your data. Speaking of time saving, if you ever tried to write down model equations in Microsoft Word, you know how challenging that task can be, right? So before we delve into interpreting model results, let me save you some frustration. Namely, the extract equation function from the Equatiomatic package, what a name, converts a model to LaTeX format, making it easier to include equations in your documents. Besides, the betas in the formula correspond to the coefficients in our table, which we'll interpret next. We interpret the slopes beta as the average change in wage for a 1-unit change in any of the predictors, while holding all other predictors fixed. There is a slight difference in how we interpret numeric or categorical predictors. Increasing the numeric predictor by 1 unit changes the estimated outcome by its beta coefficient. Since this change is permanent, we observe a linear slope. For example, in our model, an increase in age of 1 year raises the wage by $560, and this increase is statistically significant. To put it differently, every year you get older, your salary will increase by an average of $560, assuming all other predictors remain fixed. And by fixed, I mean that the year is averaged to 2006 and the salary is also averaged across both job classes and 5 education categories. The interpretation for the year predictor is similar. An increase in 1 year in time leads to a predicted salary increase of $1,100, while keeping other predictors' values fixed. Although this increase is higher than the increase in salary by age, it is only tendentially significant. This means we are less confident about it, which can be seen by the wider confidence intervals of year as compared to age. In a categorical predictor, each category is treated as a separate binary predictor, a technique commonly known as one-hot encoding or dummification of variables. For example, transitioning from one category to another can be viewed as a one-unit change, similar to the numeric predictors. However, this transition is not permanent. It represents the difference between the means of two particular categories. That is actually why we see the minus sign between the categories. For instance, if we switch our job from industrial work to the IT profession, we can expect to earn an additional $3.4 thousand, assuming age, year, and education remain fixed. Similarly, the difference between having a high school diploma and not finishing high school is only $6.4 thousand and is not statistically significant. In other words, whether we complete high school or not doesn't matter, unless we acquire a high education level. When we increase our education beyond high school, our salary experiences significant growth. Specifically, completing at least some college results in an average annual increase of approximately $19,000. Graduating from college leads to an average annual increase of around $34,000. Earning an advanced degree yields an even more substantial boost of approximately $45,000 per year. Notably, even the transition from college to advanced degree significantly raises our salary by $11,000. In summary, displaying contrasts or post hoc analysis in our results is highly informative. And if you found this video informative so far, consider hitting the like button or leaving a comment. It really helps the channel. And if you wonder why didn't we use the famous summary function, the answer is because this summary function does not make pairwise contrast by default and does not correct p-values for multiple comparisons. These are only 2 of the 9 flaws of the summary function which I described in the previous video. The Tukey correction of p-values for multiple comparisons in the table regression function is the reason why the p-value of the difference in salary between high school and below high school is no longer significant. Interestingly, the summary function still identifies the same difference of 6.4Ks as tendentially significant. This almost significant p-value serves as a typical example of discovering nonsense, also known as type 1 error. Thus, we really need to correct for multiple testing, which table regression does by default without any effort from your side, and you'll never forget it. Moreover, fortunately for us, table regression does not use the most famous Bonferroni correction. This is fortunate because the Bonferroni correction is very conservative and can overcorrect, which increases the probability of missing a discovery, also known as a type 2 error. Another question I've always wanted to know the answer to is, do the results of multivariable models differ from univariable models? And the answer is yes, the results often differ. This phenomenon even has a name, spurious correlations. For instance, in the univariable model, IT professionals appear to earn significantly more than industrial workers. Ignoring other factors, the profession pay gap seems to be 17Ks. At the first glance, this might make sense. However, when we consider education and check out the difference between these two professions in every educational group, we realize that there is absolutely no difference across any educational group. Thus, accounting for education in the multivariable model prevents us from drawing the incorrect conclusion that simply changing jobs will significantly increase our wage. It won't. In this univariable model, the job class serves as a surrogate for the education, while education turns out to be more important. The predictor year is even more interesting. The wages univariably seem to significantly increase with the years. However, when we allow year to interact with education, we'll see that only the slopes for wages in the two highest education degrees increase significantly. The rest do not. Moreover, the difference in wages between education groups is enormous. The advanced degree category reaches over 125Ks, while the lowest education degree never exceeds 100,000. This observation reinforces the idea that education is more important for wages than year. Speaking of importance, can we actually compare the importance of predictors to figure out which are the best predictors for wage?
Yes, we can.
The intuitive effect size package offers the eta squared and interpret eta squared functions, which are suited for linear regression and produce a neat little table of effect sizes. This table indicates that education has the highest effect on our salary. It's 4 times more important compared to age and 3 times more important than profession choice. I personally like to plot effect sizes with interpretation, and I think it's even more useful than the variable importance plot from random forest, which we can easily display using the variable importance function from the VIP package. The same VIP function can actually display the t-values of our linear model, where t-values can be seen as the measure of importance for particular categories in categorical predictors. It seems useful as it shows that high education levels are more important for salary. However, I don't like using VIP in linear regression, because similar to the summary function, we don't have 2 reference levels for categorical variables. This means we are missing important information and we lack the interpretation of these importances, whether they are large or small. Now, the last crucial question we need to answer is how well does our model feed the data? Your clients will definitely ask you this. 2 of the most important and commonly used metrics for assessing goodness of fit are the coefficient of determination, known as R-squared, and the ACAICS information criterion, known as AIC. Now, check this out. We can obtain all performance metrics for any type of model using the very intuitive performance function from the same performance package that allowed us to simultaneously check all assumptions with a single function. The R-squared is the most common indicator of model fit. It tells you how much of the total variance in your outcome the model explains. The R-squared value ranges from 0 to 1 with a simple interpretation rule. The higher the value, the better the fit. However, there is a catch. Adding more predictors to the model will always increase the R-squared, which can eventually lead to overfitting the model. In plain English, this means our model becomes less reliable. That's why we have the adjusted R-squared, which penalizes the model for including more predictors. Therefore, the adjusted R-squared is a more appropriate choice for multivariable models. Now, how do we determine whether an R-squared value of 0.359 represents a good or a bad fit? I'm glad you asked. We can use the effect size package to interpret any value of R-squared for us. In our case, the R-squared value of 0.359 indicates that our predictors explain a substantial portion of salary, namely 36%. The second useful indicator of model performance is the AIC, which provides a measure of the relative quality of statistical models. The AIC can be seen as the amount of information our model lost. Therefore, the lower the AIC, the better the fit, because less information is lost due to model complexity. Similarly to the adjusted R-squared, the AIC penalizes models with more predictors. Finally, when working with multivariable linear models, it's crucial to understand their additivity, which is represented by the plus sign between predictors. Remember that interpretations always include the caveat that all other predictors remain fixed. So the good thing about such additivity is that we can interpret the effect of an individual predictor isolated from all other predictors. But the bad thing about such additivity is that the interpretation ignores the joint collaboration of predictors. Namely, increasing one predictor but not changing another can lead to unrealistic scenarios. For example, increasing the number of rooms might be unrealistic without also increasing the size of a house. Being able to change one predictor while simultaneously changing another is a subject of interactions, which you absolutely need to understand to become a better data scientist. Because interactions will make your models way more realistic. And if you want to know how to easily handle interactions between any kind of variables, numeric or categorical, check out my video on interactions.